Yeah. Hey everyone. Thank you for staying in. And uh, so yeah, hey everyone. Thank you for staying in. And welcome to my presentation. It's called Threat Intelligence on Steroids, Exploits, Ransomware, and Other Threats at Scale. So the idea behind this entire presentation is I have a strong developer background, and whenever I'm trying to conduct threat intelligence or trying to find most of the things, I'm not much interested in how detection works, but I'm rather interested in how the attacker is doing certain kind of things. And that's focusing on that part of things makes things a bit easier. You are able to monitor the evolution of threats. You are able to monitor new techniques that show up. But all the existing tooling that we have for just looking at things and monitoring how they are doing things rather what they are, it's a bit limited. So that's why I've created tooling, a suite of automation tools that I have been personally using it for some time. It's a side project for me, and I've been working it for about 6-7 months now. And this is exactly what this presentation will be covering in. So before I dive into the entire thing, a bit background on me, and that will basically explain what was the motivation behind it and how I basically built that. So I am Sarthak Mishra. I work in the threat intelligence team at Sentinel-1. Great team, place to be at. And I have a strong background in reverse engineering and software development. In the past, I have created some software and made it open source, usually revolving around how to reverse malware or some config extractors or doing these sort of things. Below are my contact details, Twitter, Discord, GitHub. I'm under the name of NotDucky. So if you want to talk to me about anything or collaborate on anything, just shoot a DM. This slide is the flow of the presentation. The flow of the presentation is basically a journey through on why I decided to create another automation on when there's already so many existing, what problem I was trying to solve, and then establish a framework on what sort of threat intelligence that I'm trying to do at scale. Then finally introduce the project. It's called Harbinger. It's basically an automation to develop and identify trends on a large scale. And then using that automation, we'll be trying to accurately attribute techniques and the obfuscations that threat actors are trying to do. And using this, in the end, I'll be going through some live cases and situations where I found this automation to be really handy. All right, so motivation behind this entire project, the reason that I basically built it from scratch, another thing. So in threat intelligence, my work is usually to look at the evolution of threats, not just what the malware or the exploit is doing on the system, but rather how it's doing that. So let's say if a threat actor is able to escalate privileges, that's a decent thing. If you're able to identify a binary escalating privileges and you can detect that, it's a detection. But I'm rather more interested in how it is doing. For example, if a threat actor is creating a registry key, I'm interested in if it is doing by using a command line, or is it doing a system call or something entirely new. If a ransomware is encrypting files, obviously seen is ransomware encrypts file, stop that before doing it. But I'm also interested in how it is doing that, at what point it got to encryption of files, and what are the algorithms that it is doing, and all the obfuscations that are involved before that. Most of the things are working on the impact. Like on VirusTotal, there is a VT module. You can basically write a query to see particular registry keys were created, or if a particular file was dropped. You cannot actually work with things like how it is doing that, what sort of syscall are being involved, what sort of arguments are being passed into that, and maybe derive our logic into that. And second, the thing that I'm mostly kind of annoyed with is packers. I write a decent Yara. It works on the core malware. Then one day the threat actor decides that he's going to pack it. Now I have to work with the packer. I have to maintain two sorts of Yara or the detection rules, one for the unpacked one for the packed one. The obvious solution for that is go for the dynamic detection. But on the dynamic thing, if the threat actor one day wakes up to decide, yeah, I'm not going to do certain part of the TTPs, or I'm just going to tweak it a bit, my rule is again broken. It's hard. But what threat actors don't usually do is change their entire code base. They are lazy, just like us. They will be making constant tweaks, changes on how they will be doing things, but they rarely build anything from scratch. And I think that is substantially viewable by how many forks of open source threat tools exist. Like even ransomware, it's a simple thing to build, but yet people fork the open source Golang ransomware and other tooling. So that was the idea. I want to identify techniques on how they are doing things, and if I can use that to create some attributes So before that, I wrote some problems, and before I've been around the block, and if you want to hear about why Intel Pin is not really the great choice or want me to go on a rant about that, meet me after the conference, just hint at it and I'll descant on it for 20, 30 minutes. Why forked version of Cape Sandbox and not just, Cape Sandbox is a pretty nice sandbox. It works decent on currently. It is one of the best open source sandbox right now. It has its own unique debugging and dumping capabilities. So the reason I forked that is I wanted to have some, I wanted to extend some of the features. For example, the rule scanning ability, the C interface that I previously described, I wanted to have that. And the second, I wanted to tweak out the dumping mechanism, the unpacking mechanism that the Cape follows. I had a decent amount of heuristics that I collected over time. I wanted to implement that. And thirdly, the data for Cape that is streamed from Windows Sandbox to their server, and Cape uses an agent.py that needs to be on inside the VM in order to execute that, and it uses RPC in order to stream collected artifacts directly. I just wasn't in agreement with that. That's why I changed all of that, and then I realized instead of using Cape, why not fork that and use it from scratch. The second thing, I think this is what most of you will be interested in here, is the rule engine. So rule engine is really nice here. First of all, the reason it does that is there are two sort of rule sets that I'm maintaining: hunting and attribution detection. So hunting rules are standard that you can run on post collection of data. For example, the samples have been executed, all the data is stored. Now you want to do something like a retro hunt or something like a live hunt on VirusTotal. So you can do that. You can simply queue a rule, get notifications whenever it is triggered, and have a collection of the files that match your rule. The second type of rule is the attribution rule set. This is very similar to how Kepa rules exist. Like you can write a rule on a particular technique and it will have that migrate TTP for you, so you can cluster that further. But the reason here it does better is it's basically an expose C interface. As you can see in this C program C function that I have added here, this is something usually people wouldn't hunt for. It is a device handle fail. So whenever you're working with BOID, bring your own vulnerable drivers that tamper with the EDR agents and defenses on the system. You are usually interested in what sort of driver it is able to load. But when you're working on OSINT sources, you usually have the user mode component or the driver. And if you run the user mode component without having the driver, the device handle would fail. So this C rule, you can actually see it actually works on the return value of the call that is executed, and then answers that the file handle is dereferenced from a global list of file handles that is maintained, and it uses the NT-device IO control syscall just to return that this particular device handle was tried to be allocated and it failed. So it's a nice information to have, like a particular binary was run, but it failed to do that. So even failure here gives us some useful threat intel. Second, unpacked and packed memory dumps are treated the same. So if you want to write a bit of a traditional Yara rule, which uses few assembly bytes or standard strings, you don't have to worry about packers. You simply write that Yara, put that in, and it will work for both the packed, unpacked, process injections, and any sort of standard memory obfuscation techniques that you can think of. Then there is Yara post and pre-processing. If you don't even write a packed Yara, the rule engine is smart enough to identify by comparing the pre and post memory to identify if a particular sample was packed or not, or if the unpacking actually reveals some more data about the malware, and it automatically adds a tag for that. All the features that I'm explaining, I'll get into more depth with a use case example that I have here. And all of this will make a lot more sense when you'll practically see where I have used these features in a real life situation. So last thing that I talked about is I want to do things but at scale. When I say at scale here, I'm not operating at a huge level here, like ingesting thousands of files every day. But I have a decent server with a terabyte of storage. I'm ingesting about 100 files a day, and I keep that for a week. And I'm able to already identify some useful trends in that. So the life cycle of sample ingestion that I'm following here is pretty simple. I have integration with OSINT feeds. For example, Malware Bazaar, Live Hunt from VirusTotal, or any sample that you can find. You can even have crawlers crawling the web, find some open directories, pull those samples in, feed that here. Then the detonation happens automatically, where it is run into Dr. Play, which is the sandbox we have. It collects all sort of execution artifacts and those sort of nice things. Then it runs the rule that you have. Then at last, all the artifacts are stored in a searchable format. So all the frequently accessed artifacts, such as the system calls, process trees, process injection, if that ever happened, is stored in a PostgreSQL DB. So you can do fuzzy searching, you can quickly pull some stats from it, and all the blob data, like the memory dumps that is happening if a certain file was dropped on the system, or if something related to, other than that, related to memory happened, it is stored in a blob format. So you can run Yara or any other sort of pattern matching that you may like. So finally, let's get to the real life examples where I have been using this. CLFS exploits, common log file system. There have been a lot of these, and they are pretty consistent. Whenever they happen, they tend to stay around for a time. For example, since 2019, there have been about 10 of these, and MyTrace catalog has reported them to be actively exploited in the wild. So this scenario rightly explains the type of situation I was trying to handle. For example, detecting the exploitation of CLF exploits is pretty straightforward if you don't think much about it. All it does is escalation of privilege. There are a bunch of BLF files or log files created in a public directory. You can simply write artifact-based rule, like if several of the files are created in public directory that are BLF files or log files, then suddenly a process token is stolen and escalation happens. It might be related to CLF. But here in this example, from threat intelligence point of view, what sort of exploit is used? For example, is it the 2023 exploit? It could mean that the ransomware gang involved here is Nokayaba. That means that if this exploit is in trend, I need to be monitoring for other artifacts related to this particular ransomware group. Or if it is the 22 exploit, then it is probably the bin lane ransomware group. So now I not only need to detect if exploitation is happening, but I want more details, what sort of exploit has happened. So to do that, let's start with the easier one. Write a general rule for everything. So you can either go with the artifact-based approach if a particular artifact was created on the operating system, or you can actually look at the syscalls that is happening with particular arguments, like what argument was passed to the desired access, and if the object attribute is actually containing the type of exploitation that you're looking for. For example, here, it's a simple rule. I am basically looking for if the driver, CLFS, was actually loaded inside the memory with the NT open. And the second thing that I'm looking for, if it creates a lot of BLF files, that is the global log here. There is an OR statement. It's a regex complicated one, because writing Yara for call system gets a bit annoying with all the regeses and trying to find patterns in syscalls. That's why the C interface comes in. I'll get to that part. But as you can see in the object attributes, it's a simple regex group. It should either be global log, or it should be either be system users public directory. If any file is created under that and the frequency is more than 10, then it's likely a CLFS exploit that might be involved. But I want to identify the type of exploitation happens. So quick primer on this particular CVE. So things required for this CVE to exploit, three major calls that you need to have. First, they need to leak the kernel address to the user mode. For that, both of the exploits, the 2023 and the 2022, uses the NT query system information with a particular sort of system class information. That is OX42, that belongs to system pool information structure. So this call needs to happen in order to leak that kernel address. And second, then a lot of BLF files will be created. So here what I have written is I'm simply looking for a set of sequence in the execution artifacts of this particular exploit. So what I'm doing is I'm simply saying first the CLFS driver should be loaded. That is the first statement. And second statement is a particular name pipe should be created. Because the 22 version of the exploit, in order to trigger the bug, a create name pipe call is done. And then finally, NT-NFS control system call is done. That triggers the bug. And then later, the memory is groomed in order to exploit it properly. So basic idea here is I'm looking for a set of sequence in how the API call happens. So in Yara, it gets kind of complicated because Yara first finds all these strings and then applies the condition on them. So I don't have the proper indexes, and I have to do this weird loop thing. Easy approach here would be I simply write one long statement with endls and /ns as an approach, but you know the law of cool. I thought this rule would complicate and sell my case more. So the easiest solution here, what I'm using inside my sandbox here, is our standard C rules. In order to identify patterns, there are two things happening here. Don't worry, the code isn't complicated. It's a single one if statement. You got the syscall buffer list. That is basically a sliding window. It contains all the syscalls that are happening in the during the execution artifacts. And whenever that buffer needs to be flushed, all these rules are ran on it. This syscall contains the list of all the memory references and everything dereferenced and stored there as a string, so you can look that up. So here, writing that same exact rule is pretty simple. I'm checking here for NT query system information, the type of argument, that is the structure that was requested, and it was requested twice because once it is passed without an argument, then allocation happens, and then you get the size and you call that again. So that is there, and then I'm basically looking for NT write files in order to create that BLF files. So with this simple rule, you are able to identify the same exploit by differentiating from others. And another interesting thing about this is the NT query system information trick. In Windows 11, a later version has kind of restricted these type of structures that you can request as an unprivileged user. You need the SC debug privilege. So if one of these call fails or the threat actor isn't using this trick anymore, I know that this exploit has been modified to work on later versions of Windows, or the threat actor has spent some resource time creating these sort of things. So even with failure and different sort of results, we are getting information about how things are working here. Another, the 23 version, I went with a simple one here. The driver needs to be loaded, and all the BLF files that are created should be more than 10 inside the system directory. So with this rule, we are able to basically differentiate between them. I can quickly demo these sort of scenarios. For example, let's use this rule, the 2021 or 2022 rule. This is you simply go to hunt. This is kind of very similar to how virus total works. You can simply paste any rule, click submit, and it will work through all the artifacts that are calculated and give you back the single file that this rule matches on. Then further, I'll show you what are about the C rules artifacts that I was talking about. So all these files that are processed with certain sort of rules that are run on them during the runtimes, these tags are generated. So with this, you get a lot of information, and you are quickly able to identify trends. For example, here I have the CLFS thing. These are all the files in which CLF directory was loaded and certain files was created, and it is using that same NT system query trick. So I know that this thing is being used here, and it's a decent result. The second thing I have here is the packed attribute. So all these files, as you can see, there is a BOID tool, there is a ransomware, and there is a, BOID tool, there is a ransomware, and that's about it. So these are the file calls that were packed. So before and after, memory was differing, and it usually works. So this sort of artifacts and the rules that you are able to create, you kind of get a sense of how things are happening and how they are happening. We are not just looking at the artifacts on the operating system that a particular thing creates, but rather you're looking at if a particular driver was opened, what sort of ioctl code was sent. This is really nice when same driver can be exploited in 2 or more ways. Let's say a different primitive was exposed. One ransomware group or one threat actor is using a different ioctl, then another finds a different exploit in a different ioctl that is exposed. And it's the same driver, so you cannot rely on the artifact. But looking at the ioctl, you can write a pretty decent query on the type of thing it is been detecting. And other neat part here, as you can see, on the first one, the tag is added for the packed one, like the second tag, but the lower one doesn't contain. So your rule is working for both the samples, packed and unpacked. And this packing thing becomes annoying because another real life example that I have here is, let me open this, Medusa. Medusa ransomware group, or ransomware as a service, is pretty good. I mean, they have been recently very active. They are doing, to be honest, myriad of things. They are working with BOID drivers. They are tampering with EDR techniques with different sort of exploits. And their affiliates are nice. They have an encryptor, like they have 2 sorts of ransomware versions that I've seen so far. One is packed, and the other one is also packed, but in a different ways. You got the threshold executor, and then you got the gaze.exe. And if you reverse those binaries, they put some nice Easter eggs as well, as by padding, so the file size is increased or the hash changes. So I've been working on this group for quite some time. And the problem with this group is they pack their samples, and some of them are not packed. So you need a sort of rule where you can actually identify, like the particular thread that you are tracking right now is one day that you wake up is now packed. So a rule that actually works on both of these comes in pretty handy. For example, let's search for Medusa here. So there are 2 artifacts for these. Both of them were packed. Open any one of these detonation jobs. This is the standard Dr. Plague report. It's very similar to how sandbox, how usually normal sandbox create reports. But the interesting part here comes is the number of child processes that it creates. Other sandboxes are also able to track that. So I'm just showing that you don't have to rely entirely on syscalls. You have all these other options as well that normally you would want in a decent sandbox or a threat intelligence environment. For example, it does spawns a lot of processes, try to kill SOFOs, try to kill VSS, shadow copies, and all that. And then in the unpacked section, you can actually see the ransomware note is plainly visible, and the public key that they have is visible here. So if you don't want to mess with these syscalls, or you just want to have simple ransomware detection, like I want to track a ransomware node inside the memory, you can write that. Packing doesn't actually stop you. And here is regarding to the BOID drivers that I previously told about. So Medusa employs a lot of BOID drivers. Some of them are implemented differently. For example, the user mode component, there are 2 sort of user mode components usually in these sort of scenarios. The one that comes in an archive, there is an archive created, it downloads the driver with itself, drops them in a temp directory or somewhere, then loads that driver, executes that. And the second one is the user mode component has the driver embedded in itself. So tracking these 2 sort of things becomes a bit hard if you're simply looking at the operating system. Where does the driver came from? Was it embedded inside, or was it downloaded from the internet? So looking at the syscall makes it a bit easier. But the other interesting thing here is the, where is it? Okay. If you click on BOYD drivers, this tag is automatically generated via the C rule that I have created, and it basically checks that if a particular driver was loaded from a weird directory, for example, temp directory or any non-standard directory. Here, my definition of a bring your own vulnerable driver is that the driver needs to be bought by the malware, and it should not be present on the system. Otherwise, it's an exploit, and I'll track it in a different directory, a different category. So these are, BOID tag is a general rule which simply checks if a particular driver was loaded, and once it is loaded, what sort of ioctl was sent to that. So you get these sort of nice behavior. For example, a device handle was registered under the name of blackout, and these two ioctls were sent to that. The other quick attribution here is a different device handle was registered, throttle stop, and these two ioctls were sent to it. As I told, I'm not only interested in how the malware is able to achieve things and what it is doing, but also what it tries to do and fails. For example, here, this is a user mode component that is used by the Medusa thing. But when I found on the OSINT, it didn't have any related driver to it. So the driver was not present, and it tried to load that driver and then failed. So you actually get this handle called failed entity create file. So when a malware tries to open a file and has that handle and it fails, you can actually look at that and get an idea why the sample detonated was not detected. Perhaps it fails, or what was it trying to do that it failed to do. So yeah, these are all the runtime rules that I have created using the similar concept that I showed. The C rules and the YARA rules that are run during the execution of the entire chain that I have. Okay, didn't load. Let me switch to a local copy real quick. All right, so that sounds good. I mean, I have created a rule engine that is able to work. We are able to identify the attributes that particular thing is happening, and now we don't have to reverse each and every sample that comes in. But a threat intelligence is only as good as how diverse its sample set is actually. So if you're looking at only a particular obscure set of samples and it is showing a trend, it doesn't mean that it needs to scale out. So how does this framework scale? I've been running this setup locally for about 7 months now, and this is exactly the flow that I'm following. I have the OSINT and internal telemetry. When I say internal telemetry, I mean recursively. If something was detonated in my sandbox and the file failed, then I have a trigger that alerts me, and I can try to find that thing using that hash or some different thing from an open source feed like VirusTotal or Malware Bazaar. And second, I'm constantly feeding on the static rules that I've written or the top trending malware that are present on the OSINT. Then you have the execution artifacts and the static artifacts. They are reliant on each other. You detonate a sample. If a particular file is dropped, you pick that file, detonate it again, and you start working with the artifacts. Then we have the artifact clustering and the rule engine that basically feeds into the artifact library. And we have sort of a cohesive setup where you are able to learn a lot about the malware without actually reversing that. And simply looking at the dashboard, you will be able to identify what sort of BOYD is trending and what technique it is using. So yeah, basically exactly what I explained. I've been continuously monitoring the OSINT field and looking at the searchable library that in the end is created. Benefits of using this approach, I'm kind of getting best of both worlds. For example, I have a rich searchable execution library from the OSINT, and so it's kind of like my internal EDR with a lot more rich artifacts. Ease of monitoring is nicely done. But where it actually kind of lacks support is proactivity. So my feed is exactly dependent on the OSINT feeds. So that is highly possible that all the samples that are uploaded there is by a researcher or a sample that someone has already detected. I'm only working on the trending samples that are tagged maliciously. So right now, with the scale that I'm working with, I cannot actually process each and every file. That's why this is a downside. But other than that, we are ticking all the boxes. We have a decent monitoring rule flexibility. You can write a decent rule in C, or you can use the powerful pattern matching of Yara. You have ease of monitoring, a single dashboard where everything can be looked at. You have rich execution artifacts, which you cannot have because rich artifacts comes at the cost of performance. So sometimes your internal telemetry from the EDR that you're working with or the sysmon that you have installed on your internal environment might lack the syscalls and the Win API dumps and everything else that I'm doing. So we are winning on that, and it's a pretty decent solution. But again, right now it's limited. So the next thing that I want to do is I want to leverage the power of Kepa. I'm using Capemon, but I have modified that so the already existing integration of Kepa plus Capemon that Google Summer of Code under Google Summer of Code was created isn't really working. As you saw, the UI is a bit primitive. It leaves a lot to be desired. And the second thing, I want to extend a lot on the network capturing capabilities. I want to have similar approach like I have on the execution artifacts and syscall, but same for the network. I want to be able to extract certificates if it is using something like PKS or pre-shared key in order to obfuscate the network. I want to, because I already have access to the syscalls, I can directly extract the certificate, use in man of the middle, or have a decent or use simple approaches like man in the middle proxy to decrypt the traffic. Second, in the long run, I want to make this project open source. So everything that I'm doing right now, the code base isn't really good. That's why it's not public yet. But I intend to host a public version for it so people can go and submit samples on it real quick in like 2 months once I figure out the infrastructure. And in the long run, I want to make the entire process open source, have another decent sandbox in the open source ecosystem, and have a decent API for it. So you can have a sort of searchable library for all the execution artifacts and flexibility on the OSINT. So yeah, about 30 seconds, right on time. Conclusions. Harbinger rules can reveal interesting insights when done right. C rules are really nice to implement logic that Yara doesn't allow you to do. Some limitations are there. And second, threat intelligence with emphasis on the technique rather on the impact it is having leads to real nice insights on the technique that is trending and other things. So yeah, and we go. Nice. Thanks,
we'll take
everyone.
One quick question while Estelle and Olivier are coming closer.
Okay.
Over there.
What was the main reason why you created rules in C instead of using built-in Python signatures?
Mainly performance. I want to have those rules execute during runtime and on the buffers that I'm creating. So if I write them in Python, there is a lot of overhead involved. And I want to have, because anyone who is writing a rule similar to this must be already familiar with C and some low level. So that's why I went with C. I was thinking of using Lua, but C was the best solution that I thought. It's fast performance, and I can use very easily threads in the same code base.
Thank you very much.
Thanks, everyone. Bye.